Okay, folks, here we are. I'm going to run through how to do this one last time. For anyone who's missed it, anyone who doesn't get a chance to catch up. Okay. K expression are always products over reactants, products over reactants. We only include aqueous, we only include gases. So what does that mean? These guys are cut out. What is our answer? So raised to the power of the coefficient. So we need a there. No. Correct answer is C for the first one. Second order reactions. Look, there's two parts. 1 over A sub T equals KT plus 1 over A sub 0. Half-life is 1 over K A sub 0 equals T1/2. If we're given A sub T is equal to 0.1 and A sub 0 is equal to 0.45 and T1/2 is equal to 20 seconds. Can we find our T? So the first thing is rearranging that equation to solve for K. K equals 1 over 20 times 0.45. You do that, you get 1 over 9 is your K. So 0.1 repeating. Next step, with that in mind, you have a K. Plug that in up there. You have 1 over 0.1 minus 1 over 0.45 equals 1 over 9 times T. You do that, you get 7.7 repeating equals 1 over 9T. You multiply T to the 9 to both sides. You get, the answer is, I do believe 70 seconds. 7 times 9, yeah, it's 70 seconds. So the correct answer is C. 2 C's in a row. What do you do? Moving right along, number 3. We compare two rates, the reaction rate of 1, reaction rate of 2. So the rate of 0.47 divided by its coefficient equals the rate of Mn2 plus divided by its coefficient. What do? Multiply 3 to both sides. So times 3, get that divided by 5, that. So 3/5 of 0.47 is 0.282. So the correct answer is D. Determine the rate law on the K. To do it properly, you look at these two reaction rates and these two reaction rates. When H2 doubles, H2 goes, H2 doubles. So you have, that's 2 to the N. The rate, 2.46 divided by 1.23 happens, it doubles. So N must equal 1. When NO doubles, and NO doubles, so you have 2 to the M, we have 4.92 from 1.23. What is that? That's 4. So M must equal 2. Right there, because of the way this is worked out, the only one that has a 2 and a 1 is A, so we don't have to find the K. It's already worked out for us. However, one way to check this is to plug in experiment 3 to all the rates. Only the ones that are correct will get the correct rate. So experiment 3, C, D, and B should not give us the right rate. However, please note, if more than one of them give you the correct rate, check another experiment. No two experiments will give you the same, basically the correct rate will be correct for all 3 experiments. The incorrect rate may be correct for one experiment, but not for all of them. Okay. K expression. That'll write our K expression. So our K expression, products over reactants. K equals N2 squared times H2O to the 6th all over NH3 to the 4th and O2 to the 3rd. You plug in your values. So we have 150 squared times 125 to the 6th all over 0.3 to the 4th and 0.1 to the 3rd. Plugging in those values, you get D, a really large number. Another K expression. Remember, we don't include the solids, so this gram quantities, not useful. So our K expression is just H2O times CO2 over HCl squared. Plugging that in, 7.5 times 16.7 divided by 3.25 times 10 to the negative 4th squared. That whole thing's squared. If that whole thing's not squared, it's going to goof up. You do that, you should get another 1.19 times 10 to the 9th. Another big number. Which direction will the reaction proceed? So this one, I'm given a K. So that's essentially 1,000. And then I'm given reactants. So our K expression, or Q expression that we're solving for, Q equals cobalt tetracyanate over cobalt 2 times thiocyanate to the 4th. Everything else is to the 1st. So with that in mind, plug in our values, 0.0018 divided by 0.056 times 0.0482 to the 4th. Doing this real quick, you calculate your K. Now, the only way more information would be needed ever in a problem like this is if you're not given K or you're not given one of the reactant concentrations. But other than that, there's no reason D should be an answer. So 5935, say Q is greater than K. Q is greater than K, then it heads back towards reactants. Q has to go down. If Q and K are equal or close enough to equal, then it's at equilibrium. Okay. If the K of the reaction is 3.5 at 25 degrees, the activation energy is 20.5 kilojoules, what would K be at 0 degrees? This is an Arrhenius equation, much like the Clausius-Clapeyron of chapter 12, the Arrhenius equation that says ln natural log of K1 over K2 equals E activation energy over R 1 over T2 minus 1 over T1. So we're given is, I'm going to use K1 as our unknown. T1 is 0 degrees, which I need to convert to Kelvin. K2 is our 3.5. T2 is 25, which means 298. Our activation energy, you have to make sure to convert this into kilojoules. So 20,000, convert this into joules, 20,500. And R is 8.314. So plugging that in and solving. Plugging that in and solving, we have ln k over 3.5 equals 20500 over 8.314 times 1 over 298 minus 1 over 273. Now, the first thing we should note, because the temperature is lower, it should be a lower number. But because it's only 25 degrees lower, it shouldn't be super mega low, but it should be, the hard fast rule is about for every 10 degrees we go down, the speed should half. Well, so that puts it somewhere either A or D. We do 20,500 divided by 8.314 times the difference between 1 over 298 minus 1 over 273. You get negative 0.75. So negative 0.7577 equals natural log K over 3.5. So the next thing we have to do is inverse log that and then multiply by 3.5. You multiply that, you get 1.6. So the correct answer is A. However, the hard fast rule can immediately eliminate C and B. So if you don't know how to do this, you can at least better guess it by figuring out how much temperature is changing. Now, rate law, this one's much harder than, say, I might ask you. If we ignore light in the rate law, what is the following mechanism? So the rate determining step is what controls our reaction mechanism, which is what controls our rate law. If the first step is slow, the equation will be simple. So it's just that. That rate law is just rate equals KO2. The second one would be like rate equals KO and then O2 and then M. And because O is an intermediate, that would further throw things off. So if the second step is slow, the equation should probably include all reactants and be incredibly complicated. If the first step is slow, the rate law should be relatively simple and only include what's in the first step. So based on the slow first step, the answer is D. Last few problems. If the half-life of a first order reaction is 12 minutes, how much would of a 1 molar sample would be left after 1 hour? Since it's an hour, we need to make sure they're in the same units. 60 minutes in 1 hour. So ln 2 over K equals T1 half. So ln 2 over 12 equals K. T1 half is our 12 minutes. There's our A sub 0. So ln 2 over 12 gives you K of 0.057. ln A sub T over 1 equals negative KT. Negative KT, so negative 0.057 times 60 minutes. We want, that's units of 1 over minutes. We want that to be minutes. So minutes and 1 over minutes cancel. 0.057 times 60 is negative 3.46. We take the inverse log. Inverse log of that is 0.46, and you get 0.031. However, another cheap way to do that in a first order reaction rate, the half-life is known. Half-life is 12 minutes. How many times does 12 go into 60? It goes into 65 times. 5 half-lives would be 0.03125, or C. How do we convert Kc to Kp? The reaction is Kp equals Kc times RT to the power of delta N. Delta N is the moles of gases. How many moles of gas change? How many moles of gas change? So once again, we can't include that guy. It's a liquid. So we go from 3 moles here to 5 moles here. So delta N, 5 minus 3 is equal to 2. So with 2 squared. So this particular one, there's no numbers. But if you had numbers, you'd plug in Kc into there. R would be 0.08206, and T would be temperature in Kelvin. Which of the following changes would result in a shift to more products? So can't really include water because water's not in the K expression. So adding water is not really going to change things. Decreasing the pressure. When you decrease the pressure, we shifts to less gas. So more pressure shifts to more gas. Or what's more gas. When we decrease the pressure, it shifts to more gas. When we decrease the pressure, we shifts to less gas. Pressure is proportional to solubility or molarity. So high pressure, highly soluble. Low pressure, low solubility. So it's going to escape back in the gas phase. So it's not B. It is negative. So this is exothermic, which means heat is a product. You add temperature, you're adding a product. So it's going to shift towards reactants. The only thing left, and this one was extra tricky because of this factor, it's because when you add a base, what happens to an acid? You form water and a salt. So, and if I remove the product by forming water and a salt, I am generating a removal of product. So the reactant wants to dissolve into water to form more sulfuric acid to replace it. So D. Answer is D. Last problem is an ice problem. So cobalt hexaaqua complex is mixed with aqueous chloride to form blue cobalt tetrachloride complex. Following complex equation. Once again, you can ignore the waters. K expression is going to be this: cobalt tetrachloride over cobalt hexaaqua times Cl minus to the 4th. Now, if I initially mix 0.21 with 1.0, and at equilibrium, we get 0.054 molar product. What is K? Well, this is going to be plus X. This is going to be minus X. And because of 4 chlorides, minus 4X. We have 0.21 minus x, 1 minus 4x, and this is just x. Now that I know x, I can calculate my various concentrations at equilibrium. So this becomes 0.156. 1 minus 4 times 0.054 means 0.784. And then I just plug them in. So 0.054 divided by 0.156 and 0.784 to the fourth. 156 0.784 to the fourth. I do believe it's 0.916 or 0.92. Correct answer is D. Expect at least one ice problem like that. Well, at least one ice problem. Okay. So that is how I work through the test. If you missed it in class, there it is again.